Is it negative?
No, negative 1/2 plus 1 is positive 1/2. Okay? All right. So we're going to talk about kind of a really big theorem.
Fundamental.
There's a nice and dramatic meaning to it. Fundamental theorem of calculus. It's actually broken into 2 parts. I'm going to write down both parts first, and then we'll talk about each part.
Is that g of x?
This is g of x, yeah. You don't need to make this any harder than it is. Keep it nice and simple. So let me talk about part 1. T in this case is what's often referred to as a dummy variable. It's just sort of a, we're not going to use the T in any way, except it's just sort of a placeholder until we can get the real variable going for us. This is showing that a derivative and its antiderivative are connected. And we already know that. We've talked about that. Some of you have taken this class, so you definitely know that. Let's do a simple one. So we're going to do part 1 first. By the way, I haven't made this super clear yet. Whatever, the d whatever it is, that variable is the most important variable. And eventually we're going to transform it from x or t or whatever it is into a different variable. Anytime we do a transformation now, we have to account for, this is called an infinitesimal. Because it's super, super small, right? That's our delta x that we were doing the numeric stuff before. So we'd be given a problem like this, then we would say find g prime of x. And the answer is that. Don't make it harder than it is. It's just that simple. Notice I didn't do a derivative. I didn't do an integral, or an antiderivative, I should say. We okay? It'll get harder, don't worry. But for right now, it's this simple. Could you please find G prime? When you get an answer, share it with someone, please. That's it.
Did you vote? You didn't vote? No. I'd go in there.
We okay? Actually, let's make it t to the fifth. Yeah, the x squared's going to throw. It's going to mess with us a little bit here. So let's talk about this for a second. Notice it's not matching up with the theorem. The theorem says it's going to be a constant up to the variable of interest, or domain variable. So I can't directly do it. What I can do is I can do a substitution. Du over dx equals 2x. I'm going to transform this from 1 up to u. What's the word lead? Uses the same notation, which is great. So now what I'm going to do I'm going to take the derivative with respect to u, and that's good for us. My variables mixed up. And now we're going to convert everything back to x. U is x squared. This whole idea of substituting with the letter u is going to come back quite a bit, actually. A lot. harder than it is.
So we're using U to bridge the gap between the
We're going to transform it so it matches the theorem.
Right. Okay.
But to do that, we got to compensate.
Okay.
With all the infinitesimals. Actually, it's a little inappropriate for me to have that there, but that's okay. Because I have it here. Notice the D is canceled. Yes.
Can you run through it real quickly one more time?
Sure. So we need to transform this into just a variable, which we can do. So when I take the derivative of this, the theorem comes into play. Because it's just up to the regular variable. The thing, though, is I have to include, notice if I switch these two, du over du is just 1, and d over dx is the actual derivative, so I haven't changed anything. It's all the same. So using the theorem, this just becomes u to the 5th. Like we've been doing, right? It just becomes that with x's. But now it's doing this with u's. And now we've got to transform it back. U to the 5th, u is x squared to the 5th, gives me x to the 10th. Du over dx is 2x. And then I just combine them up. Nothing more fancy than that. Yes, sir? The same way we make the x, the t and x. It's the way the theorem goes. I'm sorry, I should derive this theorem before I show you the proof and everything. It's in the book, but it's not available. Let's do another one.